All right, let's get back to our topic. The GAN, I've done a couple of things in the meantime just to check. Things haven't improved that much. Now I did another run. See, this is still not, I wanted to keep it as simple as possible, but maybe, and sometimes then it's too simple, right? Training is just one factor. With regard to the data, I've made this sure. Here now, you see that this looks much better than what we have seen before, but overall it remains, and you can read this also when you for example ask Perplexity or GPT that these models in particular, when you want to attack something that is realistic, demanding, that they need a ton of training. But we see here already now from the result, I have changed a few things here, not that much, not nothing, or should I say significant from what I had before, just to make sure that all the references work as they should. I have copied the train models method and have changed it now just to see whether I'm missing here and there with all these names and underscores and whatever. It's sometimes difficult. And we see it doesn't look perfect here, right? From the peaks, the highs here, the lows of the returns from that time series. Also here, the distribution doesn't look like magic, right? Where we say, well, this is almost exactly getting the, I don't know, something is with the projector today. It's making me nervous. Must make you nervous as well. Do we have a stick or what? Where we can It's usually a physical issue, right? I don't think that I can do anything here, right? This is just a projector, kind of. No? I don't know. I see it just flickering out of a peripheral point of view. Also, this chart doesn't indicate that it's kind of like perfect, but that one now gives us, I would say, a better feeling. If this is now the best thing in the world, in the sense of successfully generating synthetic data, we can debate, but it seems to be, at least much better than what we have seen before. Among others, I've said I haven't changed that much, but given that we have had the time during the break, I have increased the number of training episodes for that. That's for sure a factor here that is important, no matter what other factors are, like the capacity of the... Oh, this is making me nervous now. Seriously, don't we have a stick? There is an umbrella. Sometimes it's just a little... Can you touch it? Slightly, slowly. I don't think it yet. It's less, isn't it? I'm not sure, but no, it's gone.
We can turn that one off, maybe.
I hope that it's not. Sorry?
Can we just turn it off and just use that one?
I don't know. I can try. I really know how to customize it. No, still. Here. Just the two of them. That one. You ask me something. Now I'm sitting here trying to, at least I was able to turn that one off, but it doesn't show the screen anymore. Why isn't it showing it anymore? Oh, sorry, that's the right one.
Not that. Okay, sure. Yeah. Your left.
Right? Is
There. Oh yeah, that one is working.
that one is the right one. Okay.
How did you get only that one down there? Okay, but it's only that project.
Okay.
Yeah.
And here, of course, what we compare all this to and say, well, this is, by definition, this is the benchmark, is the historical data set, right? So that's simply the benchmark. And just the final part here to show we can, of course, also simulate into the future. But this is nothing else now than, again, do a sampling in terms of generating synthetic data. And you say, well, this is for, I don't know, 500 periods, this is for 1,000 periods, for whatever, right? So can you now, in that sense, do a simulation, but it's not that we have a discretization as we've had it before for a stochastic differential equation. Now we have a deep neural network which has learned the trick to generate returns that we here put together to come up with our time series data in terms of at least the relative performance, cross performance normalized to 1. In that sense, it is for sure not the same, but in the spirit it is similar and close to our option pricing example that we have, where we say, well, there's a geometric Brownian motion in a Black-Scholes-Merton model. We have 5 parameters and we generate prices, and based on supervised learning, the deep neural network has learned to price options. We have seen that with out-of-sample options, this might not be perfect, but this can improve for sure. And the same holds true here as well, right? So we can use a deep neural network to learn about the distribution of a time series data set and then generate, in our case, log returns that are similar to the original ones, again solving the problem of limited data. As before, the same conclusion can be made. We now have infinite data, can generate 1 million, 1 billion, whatever. This is what you often simply need for reinforcement learning algorithms to get good results. Yeah, I want to leave it as it is here. For me, myself, I haven't been doing that much. I haven't just started, to be honest, recently with that topic. This is still a work in progress. I always, basically, whatever I try to conquer in terms of a topic or a subdomain or field, I try to come up with the most simple examples I can come up with. So therefore, I first got started with this time GAN thing, and I had an implementation. But I said, well, this is all, it was much too complex for me, right? It's like giving too much input at the same time is not good. Therefore, I was trying to boil it down, but often, like maybe in the sense of Elon Musk, I don't know who has read the recent published biography, you would have said, well, if you don't need to put 20% back into something or to something, then you haven't taken off enough beforehand, right? So he was saying, well, we, like with one example, obviously X.com or Twitter back then, firing so many people, and now they are hiring back people, right? This is exactly what he does in engineering with everything else, right? So here, maybe with such examples, that's my experience. I like to do it as I was describing, to boil it down as much as possible, but still having it meaningful. And sometimes you need to make it then a bit more complex afterwards. So this could be the case for future updates here. Maybe one other thing that maybe a tiny little thing that I want to show here is that when I create the sample data sets here, this is what I commented out when we went through it from top to bottom, is that I also have done, in the meantime, some normalization. I think there are arguments that we can put forward in this context that we say instead of the synthetic data itself, we have here knowledge about the original data, that when I create synthetic data, I do a normalization. Then, having a look at the numbers, not a big surprise, I match the mean exactly, and I match the standard deviation exactly. So I normalize based on the two first two moments, right? This changes obviously the complete data set, right? If it makes it that much better, this is debatable, but what I wanted to show, and this is what I mean, this is arguable from my point of view, in that case, the average at every single synthetic data set starts at the same point and ends at the same point, right? This is now a numerical consequence, if you like. This is an implication because for the very simple reason that I've set the average log return, and they are additive, I've set it to the same value, right? So when I add them up, I always end up at the same value, no matter what synthetic data set I have, right? And this is a little bit related to the subheader that I had on the slide, right? Here, what has been, right? We have our financial time series in the past. That's a given. And here, what could have been, usually when you have something generative, a time series, you want to do it into the future. When I do this normalization, for me, this would be a case where I say, well, I have this starting point at 0, whatever the date there is. We could add this as well. And here we have the endpoint that we know, like boundary conditions. Here we have not just one initial boundary condition for maybe a stochastic equation, differential equation. We have two. We have the initial point fixed and the endpoint fixed. And what is in between, this is open. So what could have been, right? We know the start point, we know the end point. This is like somebody, I don't know, leaving New York by car and driving down to Austin. There are, I guess, a couple of options. Overall, right, it is like, you know, probably how this looks, but yeah, probably a couple of things left and right, you know. You go to the gas station, then you get your burger, right? So that's my thinking now, right? I haven't seen something like this or these arguments from others or in other papers, but it's easy enough to simply add this normalization and you have a completely different situation now. If I don't do this, this is what we have seen. We have open-ended. Here is, if you like, closed end, closed beginning, just one value, closed end, also just one value. And here, that's that particular part. It's just this one comment here that I can take away or change that line. And then we are back in the other game here. And now that I have repeated this exercise, you see, obviously, every time I generate synthetic data set without having fixed the seeds, etc., I get different, like with Monte Carlo simulation, I get different paths here, right? The other data set looked for me, a little bit better, simply visually. All right. Maybe let me check. I think I've done a few changes. I've simulated a few, changed a few of them.
How many of you guys are going to be able to make it to the barbecue thing? Four? In advance.
Not too many for all that food. Don't you think you can?
5, 6.
Don't you think you can call them
I
and
did.
yeah?
I already told him, and so I told him 20. So that's fine. 20 is fine.
They say it
We
though.
pay for, normally they say the minimum is 45.
Okay.
So that's the only reason it's for 45. But I didn't think we would have 45 there, but I thought, oh, we'll have, you know, if we have 60 at the workshop, we'll have 40 there. And this is too big a difference. And so I did. That's what I was just now doing. And they said they would give us a break and pizza for 20. And we can just all sit in a big empty party room. But there will be, Hyung's coming. I think he's bringing his son, and then you're bringing your wife and father-in-law and your son. I know. This is what happens when you have a party nobody comes to. It happened to me last semester, didn't it? MSQP students do not party, apparently.
They are just
They're unlike
mastering
dance
micro and finance and yeah.
unlike dance professors, just, if any of you are thinking about being a dance professor, just telling you, you're going to join the party.
Great. So now the question is that we have infinite amounts of data. So we are focused on time series data. What do we do with it? And here's now one application that I mentioned before for the hedging of options. So we now know quite a bit already about environments because we have worked with the environments before, like the two of them, noisy data, and we turned the one, oh, okay. Turned the one thing off because this was flickering all the time there.
On.
Yeah. Somehow I didn't.
Wrong.
Oh, that's the wrong one. Yeah, so here I introduce yet another one because the two of them, they belong together, so to say. And that's from another context as compared to what I was showing before. So the environment here is about options.
Sorry.
Now pricing is hedging. And as before, I want to make sure that the API is in line with the standard for OpenAI gym environments. Here it's observation space, action space. Yeah, just simple helper classes. Helper, I mean here they help out in making the API consistent, right? Apart from that, this environment now takes as input the 5 parameters of the model. Here 0, k underscore, etc. And the are stored, the parameters, the arguments are stored here as instance attributes. Also the number of steps, because we are going to do a simulation like we did before. So number of steps, 50, 500, whatever we consider appropriate, is what is getting simulated. But here we are in the canonical standard model, the Black-Scholes Merton model. Doing the simulation, you see it down here, short rate minus a half, the volatility squared times the time delta volatility times the square root of the time delta times a random, here normal distributed factor for the Brownian motion. So overall, this should give us a simulated geometric Brownian motion, right? So what is happening here now, you might have noticed when I mentioned, we have as input parameters, we have here the 5 parameters. 2 of them don't have an underscore, 3 of them have an underscore. So this is still, my goodness. Didn't we turn this off before, right? Janet, can't we turn this off somehow? This is like, because this is flickering all the time. That's.
I thought we had it off.
Yeah, it was before. It was somehow, but.
Display.
But this turns off.
Advanced controls.
But this has been turned on again.
Off.
No, it's
wrong.
It's the other left.
See, I don't know if it's this way or this way.
Yeah.
Okay, why didn't you come back on?
Yeah, this is.
No, come back on. I'm sorry. We were supposed to not have problems today. Those are like the PC controls. So this is display.
That was
Supposed to be on. Did you want this on?
I don't need it, but.
It's projecting yours, right? Okay, read that. That's supposed to be on there. What does that say? Primary extended.
Display, I think display needs to be turned on as well. Without display on, it doesn't work.
No,
Yeah.
it's going to turn both of these on. Right projector.
That's right. Yeah, now we have it here. No.
There, that should do it.
Then, yeah, but the left one now is, what is it? Extended
No,
PC?
That's the PC.
Yeah, but
that's this.
it goes via the PC. Yeah.
That's this. What are you trying to do?
Yeah, it's not projecting.
Oh, because it needs to be.
No.
Laptop. Mother, father. Oh. Why aren't you off, projector? It's so weird. How'd you turn it off when you turned it off? You don't know. Who did it?
It was random
Oh, just
clicking.
clicked until you got it.
Now it's at least doesn't have the issues anymore.
It looks like it's not flickering at the moment.
Yeah.
Let's just try to get through launching it off and
All right, we hope for the best here. So again, we have like 3 parameters that have an underscore. This is supposed to indicate here that we can pass several values for K, R, and sigma, right? So when I was saying here, the simulation takes place for geometric Brownian motion. We have here strike short rate volatility, which up front is chosen randomly from the set of values that we pass. So the initial value is fixed and the time to maturity is fixed as well. We are not having stochastic volatility, but I allow for a random choice here for the volatility value. It doesn't have to be if we have just one value, and then I can only pick the single one that is in the iterable there, right? So as usual, we end up with the data frame, which here has now, like in the simulation class from before, stores the single simulated stock price process, or whatever we want to think of it. So in that context, since we are interested in European call options on a stock, would be a canonical example. So there we get the ST value from in state. So the question is, how do we describe now the state of the environment? Before it was, like I mentioned this a few times, like in supervised learning, we have like 4 historical log return points, right? Here we do it a little bit differently. We have ST for hedging, obviously irrelevant, right? It's the stock price at a certain point in time. Then we have the time to maturity. This is not stochastic. This is just like something that gets shorter. But for hedging, theta, right, might be an important aspect. And we have the call option price itself. So you see here the array that is collected there is ST, TTM, C, it's stock and bond. Let's see here, where do we have it? Yeah, it's not yet there, sorry, sometimes. No. I was looking upwards, but we come to it, and I just wanted to make sure that I don't jump over these elements. And the stock and bond attributes are passed. Seed here just for compatibility, consistency with the original APIs that I have in mind here. And then we have the reset. And here you see there is 1, 2, 3, 4 things that we set to 0. Episode set to +1. We come from 0 is set to 1. Then simulate data. Where is it happening? Up here, right? It jumps here, simulates 1 path before it chooses randomly the parameters as discussed. Initial value is always the same. No randomness here included. And then it returns the first state. So that's the starting point. Then we have the step here, right? No, it doesn't fit completely on the screen here with my zoom factor. And we have 2 cases. The first case is when we are at the very beginning. Reward is 0, bar is immediately increased by 1. The stock position is set to the floating value of action. The bond is set to the state 2 value. What is state 2? Yeah, we can have a look here. This is the call option value, right? 0, 1, 2, 0-based numbering, right? Minus the self-stock times self-state 0. Self-state 0 is the stock price. So this is like in the original model. The bond is the reminder here in the portfolio context of the price of the option minus the stock position, which is derived from the delta, times the price of the stock at that point in time, right? So the idea here being that I replicate the portfolio by opening a bond plus a stock position. The stock position is given by the delta of the option at a certain point in time. The bond fills up until can also be a short position depending on European calls and puts, etc. It's the position which fills up until we have exactly the price of the option. And then we get a new state here via the helper method. So that's the, let's say, special case, the initial special case. After the initial case, which is here separately treated with, as usual, we increase the number of the bar by 1, get a new state, and here now we calculate the portfolio value as self-stock, that's the delta, times the price plus the bond, and the bond in the model here of Black-Scholes-Merton has a constant short rate, and yeah, this is what we reflect here, constant continuous short rate, right? So the P&L is simply the payoff of my replication portfolio minus the value of the option. So my replication portfolio can have a value of 100. If my option has a value of 90, I have a profit of 10. I'm not interested basically in the profit. I would like to have a profit of 0 all the time. When my portfolio pays off only 80, then I lose, in that case, 10. So in the first case, I would be over hedging. In the second case, I would be under hedging. This is how my position, and this is real world practice, right? In theory, we have dynamic hedging based on a continuous time model where the hedge is perfect when we do it correctly. In the real world, this doesn't work because we are A, not able to hedge continuously, B, transaction costs play in general a role which would make it infinitely expensive when we would trade and adjust the positions infinitely often, right? As long as we have non-zero transaction costs, we need to resort to also in theoretical models, we need to resort to discrete hedging. And then we introduce what is called the hedge error, right? So we try to be as good as possible. More sophisticated strategies then include the gamma, so the second derivative of the price with regard to the option price with regard to the stock price, in order to have second order effects also included. But that's not our topic here, right? The agent here, the reinforcement learning agent, shall just, right, observe what we give it, the stock price, the price of the option, the European call option, and where do we have the return here? Here, the stock price, time to maturity, which is deterministic, the price of the option, and the portfolio position as input. Because this is part of the state, right? This is like what I have in my portfolio is relevant, obviously, for what I need to do in terms of an adjustment of the position of the stock position, right? So here it is the portfolio, the P&L, and this relatively long data frame that is created here, right? This simply collects all the statistics, right? This is the number, the episode number, the stock position, bond position, etc. So everything that might be of interest afterwards here is collected, and for every single step we collect this in self portfolios. Here I provide alternatives. There was a question before, does it make a big difference if we change the reward from 1 to, I don't know, 5.7 or 0.1 or something else that might jump to mind? Here I'm offering a few options, right? The one that I go with here is minus the minimum of the absolute value of the portfolio over self-new state. That's the option price. Right, so that's a percent value here for the option product. This is a relative hedge error, if you like. So in practice, what we do here, we penalize deviation. So we penalize the hedge error. We could also say whenever it hits it exactly or comes below a threshold or whatnot, then XY set, right? But here it's a penalty that we return. So in that sense, it would try to minimize the loss and maybe not maximize some high score or whatever, right? So stock position, bond position. If we reach the end of the data set, we are finished, otherwise not. So here it's not like an accuracy, or we could come up with something like this as well, that we track the P&L, and we say, for example, when the loss exceeds, relatively speaking, in percentage points, a certain value, then we set it done to true and stop it. But this is simply here starting at a certain point and going until the end. So that's for sure now a slightly different environment. This is now, as the name suggests, tailored to this hedging problem. It has primarily now nothing to do with what we have been doing before. But the approaches that we have chosen before could also be translated into what we are doing here. Actually, one of the approaches is applied here, it's simulation. Same could be done now with noise or with data generated based on a GAN, right? So the hedging agent, here a little bit of a configuration for TensorFlow just for information purposes here, showing 2.11. So the code currently runs at 2.11. If it runs with 2.09, I don't know, with 2.12. So TensorFlow has a long history of changing the API basically with every release. Therefore, with this package, I'm often showing the version so that when it is recorded, when it is seen, when it is executed at a later date, we need to be aware of the fact that things might change and that the version here is relevant. So doing import, nothing specific. All the deep learning models that I use here are fairly standard and small in terms of the capacity, just sequential models with dense layers. No additional tricks like dropouts, normalization, whatever, regularization, I should rather say, setting the seeds here. And here is the DQL hedging agent. What does it have? Here, that's the discount factor for the future reward. Epsilon, that's in the beginning the percentage value for like 100% of exploration as compared to exploitation. For example, if I use these words, I've said it before in the slide deck, you find the explanations, definitions for it. I always want to retain a certain level of exploration, and here is the epsilon decay factor. So the longer the agent is trained, the more episodes it has gone through, the lower the epsilon value will become. This means that exploration, meaning random actions are chosen, is replaced by the intelligence, hopefully gathered and embodied in the form of the deep neural network. All right. Maybe I don't go into all the details here. Memory is where we store past experiences, as they call it, so past combinations of state, action, reward, and next state. Here the model is built. I mentioned it before, fairly standard, nothing special. The optimal action here is derived, and what I do here is I do like based on my numerical data, I do a optimization here in order to come up with, let me call it that way, a best guess for the delta and therewith the stock position for the hedging. All right. If you have a bit of time, you can go through the elements and check it. The standard action method is here in act, and this in turn here calls the optimal action method. Right? So here we have the differentiation between exploration and exploitation. We do this in a random fashion. So we draw a random number, and when it is below the then current epsilon value, then we simply do random sampling. Otherwise, we do it in a systematic manner and we come up with the optimal action based on the method just discussed. So replay is also a standard element of reinforcement learning agents. I've mentioned the memory object. There we store a maximum, in that case, of 2,000 experiences. And during replay, here, in terms of numbers, batch size fixes this. We do a random sampling from memory. So if the batch size is 32 and we have 2,000 elements in the memory object, we randomly sample like we have done before already or similarly done in the GAN context, we randomly sample 32 out of the 2000. And then retrain the model on these 32 past experience. I like to compare this to laying in the bed at night and ruminating over stuff that has happened during the day or in the week and say, well, this was good, this was bad, and you update your neurons and then you sleep a bit. And next day you have trained your neurons, you have changed the weights, the electrical capacity in your brain to reflect your past experiences, right?
Is that Zen Buddhism?
Is this what?
Is that Zen Buddhism?
No, that's kind of like neuroscience, right?
Okay.
Yeah, it is, adjusting the weights is, you can set a person from friend to foe or
You can definitely
whatever.
do it.
Yeah.
Don't do it.
And this is what's happening here during the replay phase. So when do we do replay? This question will be answered when we have gone through the learn method here. So we want to collect total rewards for every episode, then the maximum total reward. So we simply want to keep track what was kind of like the best run, the best hedging run. We do 5,000 iterations max. If maybe we have a break, then we do a break, right? Here the action is taken from the act method. Then we get here our 5. Here in this case it's just 4 elements. In the newer API versions it would be 5. Total reward is increased by the reward that we get, and before we just had this simple reward, 1 or 0. Here we now have a floating point reward, right? When I have or penalty rather. When I have a large hedging error, I get a large penalty. When I have a small one, I get a small one. So this is not incentivizing, it's punishment here. And during every single iteration here, we collect what was happening. We had an initial state, we took an action, we got a certain reward, then we got the next state, and we know whether we are done or not. Right? So that's, I said it before, done here doesn't play a role as in many other contexts. Here it simply indicates we have reached the end of the data set and nothing more is to be done. So state is set to next state, and then we repeat this until we reach the end, and then there is a bit of an output, and we break and start all over. And here is where replay is called. When we have enough memorized experiences, meaning greater than the batch size, then we do a replay, so that we, after every episode, we do the replay, another episode do the replay, another episode do the replay. So there is a constant updating of the policy going on. But still, we have always like exploration, exploitation, so there are a couple of factors here at play. The last method is the test method. Test method separately for the reason that here, I only take an optimal action. I'm not working with the act method anymore, which also gives us random actions, random updates of a position, right? Here only optimal, and I put this in double quotes because optimal given the then state of the deep neural network, right? So this is like for a tennis player, this was the best that I could do, but it could have been done better, right? The same holds true for our agent here. Only optimal actions are chosen. No exploration. Right? I could also write only exploitation. And this is just to run through and see how well does it do when we are just relying on the deep neural network's predictions. So that's the DQL hedging agent. Now let's do the learning. The first here is to instantiate the environment. I call this simply stock. not giving it a name. Starting value 1, then I have here different strike prices. 2 are for out of the money, 1 at the money, and 2 in the money. A certain starting point. Then we have the selection of potential short rates, 0, 1%, 5%, and the selection of possible volatilities, 1, 1.5, or 10%, 15%, 20%. I'm not setting seeds here. DQL agent is instantiated, 250 episodes, and as my son used to say, Luditz, los geht's, ready to run here. When you see the total reward here, I stick to the typical terms and expressions used in a reinforcement learning context. That's more or less here the loss, the accumulated hedge error, if you like. Right? So the best is -3. We've seen much larger values, and the hope, of course, is that over time this is getting better and better, but there is no guarantee, in particular at this very early stage here. When we still have a lot of exploration, we shouldn't give that much with regard to the numbers that we see here, right? When we have a pretty good result, like here the best one, at this point in time, this might simply be luck, right? And the others, right, given several mishaps in terms of the random actions that have been chosen, this might give us a really bad output, a really bad result in such a context. Right? Maybe I should have better set this to a shorter period. So I don't want to wait this out. Maybe there's also something for break. So let's say 60 roughly would be good enough for us. Pretty long trace back here for the keyboard interrupt. So at this stage, related to what I was saying, we are still at 74% exploration. So 3 out of 4 hedge positions are generated randomly. That's for sure, I would say that it's not like the best hedging strategy in the world. But let's do a test here and let's see how it looks. This here and now that I see that I have saved two pictures, I have used them here. I think I've mentioned this article yesterday with regard to Goldman Sachs using AI in the context of complex derivatives and their pricing and their trading, right? So here is if you want to sign up. I enjoy what Matt Levine is doing there. It's pretty interesting.
Scares the hell out of me.
Sorry?
Scares the hell out of me.
Why? What?
Because you're going to have a whole bunch of people like that student that came into my office and said he's given up on finance because he got a $5,000% return on.
You told me about that. Yeah.
You're going to have a whole lot of students, of people like that, not students, but people like that who think they know everything because they can do this.
I mean, a lucky punch is a lucky punch. You should.
Right. Well, it would be eventually, but I want to retire someday. I mean, I guess I should just put my money in cash.
Yeah, here in the slide deck you get a bit of background. Most of you probably have heard and know how this works in principle. Generated here with Perplexity. I think you can notice that. Here the testing now gives us -15, -20, -11. So now it is a little bit of trickery that is done here. The environment, I take out or show here a couple of portfolios, right? Over the hedge positions, they have all been collected there, right? Here you see in this one long data frame, this is like episode 36, which is the the last one before I clicked the keyboard interrupt here, or initiated the keyboard interrupt. And just what I wanted to show here, this looks like a good example, right? So what do we see here? We have the stock price on the right-hand side. Recall the stock starts at 1, and then we have the different volatilities, etc. So this is the stock's evolution. And here we see more or less going in tandem the value here of the option. This is the dashed line, and phi, which is the portfolio value. So here the differences are not that large, but there's no guarantee that this always looks like this. This is more like something, maybe with another approach that this could be established. Here we even end up with a slight hedge profit, right? So here the call option that we have seen here is one which is in the money, R is 5%, sigma is 15%, and you see here the P&L over the hedge life, right? And that's the P&L distribution. So prices are pretty low. Absolute values are kind of like small. Percentage profit and loss might be pretty large, right? Because you see on the left-hand side, these are in absolute terms the option prices, right? Therefore, when we see something like 0.01 as an absolute difference, might look small, but in terms of an option that has a price of 0.05, this is 20%. So this is where this looks so great here, right? But this is what I meant, like minus 0.01, this is here the minus 20%. Because the option price is so low in that context, right? But that case, how did I pick the case? Let me check here. Looks and portfolios phi. How did I come up with that one? Where is that P? Yeah, maybe I let it, that's probably before I change now something in the code down there. I can restart the learning, and this will add more options to it, right? Every episode adds another option, what we're doing. So that when I interrupt it, now it has dropped over the couple of iterations, just like or less than a handful, from 74 to 72. Do now the testing here again with the 3 of them. I don't know why this is doing that. And just I followed along. We had a loss, a profit, and now a large loss here for this little exercise. Here you see where all the 3 of them are going in tandem. Let's first see we have a call. The call is, did I say before it was in the money, before it was out of the money, right? So S0 is 1, exactly 1, and before we had like 1.1 or what. So there it was out of the money, here it is in the money with 5%, 1% and 10% as short rate and volatility. So here you see, typical for call option, over time the stock price increases, and therewith the option here comes in the money, right? It is in the money, it gets further in the money, that's the correct way to put it. And we see again that the hedge is not too far off. But in this case, the accumulation of the P&L shows that we are losing money in that case. Doesn't sound like that much, but again, we need to see this in relative terms here, right? So, therefore, that's the important part. The P&L distribution, and you see that this is basically prohibitive. This is 500%. That's well too bad here in this context. But overall, you see how such a setup works. We have the environment, which here is really dedicated, custom tailored to the hedge problem in terms of what it gets back as the state, etc. And you have the agent. The agent always does the same. It interacts with the environment, sees the state, comes up with an action, either randomly or based on an optimization calculus, meaning, for example, internally the deep neural network, which has learned hopefully enough to come up with sensible, reasonable action choices. And so it does it over and over again. And you can imagine now when Alpha 0 was playing chess against each other, it's basically exactly the same. But the state for chess is the chessboard plus a little bit more. Why a little bit more? For example, if you have castled or not, might not be visible, for example. So you need to provide a bit more than just the board position. But that's basically how it works. And then takes it, chooses an action, gets a reward or a penalty, updates then every once in a while, updates the deep neural network with regard to what it has experienced in the past. And so over time, after I don't know how many millions and billions of self-play operations, you get a good, well-trained agent, hopefully. Yeah, that was the hedging part here. We could play this through for ages. As I was saying, millions, billions would theoretically be possible with my implementation and hardware setup. It's prohibitively long to do a million, I would say, but in theory at least we can do that. So when I started using Python for simulations for American option pricing, etc., I always let the machine run overnight because a single valuation was taking quite a bit, and when I wanted to implement the test program, so the machine was then running. Well, this is like, I don't know, 2004 or when it was. So the machines were much, much slower, and NumPy wasn't yet around, etc. pp. Right? Yeah, that much about that part here. A little bit of background, just as more or less a visual reference. There are better and in particular more comprehensive resources. So natural language processing. Yeah, I don't know whether we should, I don't know, planned was nothing, right, Janet, with regard to lunch or something,
No,
whether we,
fine.
because this is now the
This
complete,
is a new topic.
the complete new area where I would say, well, theoretically, it would make sense to have now a break. We can move on or the break later. What would you prefer? For me, I feel like that we maybe do this after the lunch break so that we have a clear reset and then dive into the text world and leave the numbers, at least to a large extent, behind us. That's okay, everybody?
Sounds good? So we're coming back in 1 hour, so 1:30?
Yeah, great.